Okay, guys, I think we can start today's session. So, yesterday we have been discussing about ROS projects. I have gone through some of my projects that I mentioned in my book, ROS Robotics Projects. And today we are planning to discuss two topics. I'm not sure I can able to complete, but these two topics actually we have discussed some basics of it. But this is like if you want to do something on this topic, uh, we will see how to work on this. Okay, so it's like a deep dive into that topic, and I will be showing some example. Okay, so the topics are ROS controllers, which is in this chapter. Okay, and the ROS path planners. Okay, so there is one more topic which is very similar to these two topics, that is RVs and RQT plugins. So the similarity is that the plugins. Okay, so the controllers, then the path planners, then the RVs plugins, all are like kind of plugins. So I think you know what the meaning of plugin. Plugin means like if you are running a program, you can add a piece of software in the runtime. For example, if you check, I mean any software, I think in Word, in MS Word, if you can check, like there are a section called add-ons or plugins, in which you can add something on the software. Okay, so that is not there by default. Okay, so that is actually called the plugins. So coming back to the point, if you discuss the ROS controllers, I think you may have some idea about the ROS controllers, but I will give you a clarity first. Then we will see how to set up ROS controllers, what are the different ROS controllers available, then how to configure and run ROS controllers. I mean the existing one, and how to write a new one. Okay, how to write a basic ROS controller. Okay, which is also mentioned in my book. So I will be like showing that. After that, I will be going to the path planner. So these two having, I mean, mostly same, yeah, same concept actually. Okay, so let's start. Okay, so I think it will be better. For example, just a second. Okay, so I think it will be better to start from this link. Okay, so I'm just sharing this link, and maybe I can share all the links so that you can refer it later. I think it's the same link. Yeah, these two are the same, I think. Yeah, and also this. Okay, maybe I can start from here. I think I already explained this diagram before, but I can start from here. This is the starting point. Okay, so you can see the title, right? Gazebo ROS control. Okay, so what happening here is that, so if you start working on ROS, we can either simulate the robot or you can work with the actual hardware, right? So for example, if you're working with a simulation in Gazebo, what we have to do is like we have to create the URDF, and you have to mention the links and joins, and you have to mention the transmission tags. Transmission tags means it will say what kind of transmission that we are using for each joint, and we will be like updating all these things, including the dynamic parameters like inertia, mass, all these things we can put it in the URDF. So we are using this URDF to simulate, right? So how that is working? For example, if we want to move a joint, okay, in Gazebo, if we are using ROS Gazebo for working with a joint, a specific joint, how that is working is that a joint which will be actually defined in the URDF, right? The links and joins are defined in the URDF. And actually, in simulation or in the hardware, a join will be attached to a motor mostly, right? Like if you take a robot, a join may be connected to some actuation. It may be a passive actuation or like an active actuation like a motor. So we have to like send commands to this motor, right? So that's how the join will be moving. So in order to do this, ROS actually implemented some standard layers. Okay, some standard layers. So what happening is that you can see here on the simulation. Okay, so in the gazebo simulator, we have the model. Okay, we have the model that we got it from the URDF. Okay, and that model is having joins. Okay, so you can write values to that joint and you can also read from that joint. Okay, reading and writing. So we can read the state, I mean the joint state, what is the current value of the joint, and also we can set the joint value. Okay, so what ROS does is that it actually adding a controller to each joint. Okay, for example, if you want to control a joint using position value, you can add a position controller. So I think you know about the controller, right? The controller is actually like maybe I can show you the block diagram. It's very simple. I mean, let me check. Okay. Yeah, maybe you maybe heard about the PID controller, P controller. The thing is that if you want to move a joint to some degree, 90 degree or something, you are giving the 90 degree to a set point. Okay, that is actually the set point or the goal point, and you are giving that not directly to the motor, through a controller. Okay, it can be a software or it can be a hardware through a controller. So controller will be controlling the output actually. So like if you are giving a 90 degree to the actuator, okay, to the motor, imagine the motor is in 0th position, and if you directly giving 90 degree, it will quickly move to the 90 degree, right? So that is not a smooth motion. You can try with your hand. Like currently your hand in one position, and if you quickly move through another position, I mean that is not the desired kind of motion that we want in robots, right? If all the motors are moving very quickly, the robot will be shaking, right? So what we want is a smooth motion. Okay, so if you give 90 degree, there should be some kind of acceleration and deceleration that we have to give to the motor to obtain the smooth motion. Because when you start the motor and when you stop the motor, it should be smooth. Okay, so that is the main purpose of the controller. Controller will be controlling the output. Like if you give a goal position, the controller can regulate the output to, it's not regulation, like it can control the output to the actuator by taking some feedback. Okay, some feedback. The feedback can be a wheel encoders or anything. So basically you have to understand that the controller can regulate the actuator output. Okay, so it will be smooth. Okay, so that is the all purpose of the controller. So I think the PID controllers are using commonly. So if you just search for PID controller block diagram, you can able to see some P stands for proportional integral derivative. There are 3 components. So we are giving a set point, and this is output. So it will be going through this loop and then it will be controlling the output. Okay, so basically just understand that the controller can able to control the output. To maybe you can say it for smoothening the motion. Okay, so what we have discussed was in each joint of the robot, ROS can assign a controller. It can be mostly a PID controller. So that is what it is showing here. So imagine we have a joint, a set of joint maybe. So these are the controllers. So here you can see set of controllers here, and there is another block called controller manager, and then another layer called a hardware interface. Okay, I will explain what is happening. So there is a program called controller manager in ROS. Okay, controller manager, which is already there when you install ROS. And this controller manager is the program that is loading the desired controller. For example, in your robot, one of the joint want position controller. This controller manager can load that. Okay, you can just mention to controller manager, hey controller manager, I need to load position controller for joint 1. Okay, so it will try to load or try to attach a position controller to the joint 1. Okay, and the controller will be loading, and the controller is having an output, right? You can set the input at the set point, and it is also having some feedback. So what happening is that the controller here, it may be a PID controller mostly. The controller is not directly communicating to the hardware or simulation. In between that, there is actually an abstract layer, hardware abstract layer. Okay, it's called the hardware interface basically. So it's very simple. Like we have the controller, and into the controller we are giving some set point. For example, go to 90 degree, and this controller is communicating to the motor, okay, in the robot, not directly communicating, but in between there is a layer or a bridge that is called the hardware interface. Okay, hardware interface is like a robot agnostic layer. The sole purpose of hardware interface is like a bridging. Okay, so controller is not directly communicating. There is an agnostic layer. Okay, that is actually communicating to the simulation or the real robot. So the purpose of robot hardware interface is that it is taking commands from the controller, okay, the output from the controller, and it will be feeding to the real robot, and it will be reading from the encoders and giving to the controller. Okay, so there is an interface layer between controller and hardware interface. So it's actually bridging. Okay, okay, so there is a question from Bharat. So it will be use client server communication service API. It's actually communicating over actually topics. Okay, so like the controller will be like sending there are multiple ways. Actually we can have internal communication not through topics, but maybe we can inherit from this hardware interface class, and then we can we will get the controller in commands and the feedback. So I can show you, then only you can understand. That I will get back. So Tejas is having a question, sir. Controller manages a service, though, right? Controller manager is actually a node. It's an independent node. It can load, unload the controllers. Okay, it's already there in ROS. So the purpose of controller manager is like managing the controllers. You can load.
But
Yeah,
yeah, sorry,
yeah.
but according to my understanding, client server communication is nothing but a service communication. So with this only we can make the commands and get the data, right? So when you use the topics, we will just broadcasting it. How can we use the topics here?
No. What I'm trying to say is the note. I mean, in the controller manager, it is actually using like some services to load and unload the controllers in the controller manager. In controller manager and robot hardware interface, we have some classes actually. We have some classes that can talk to the controller through some APIs. It's not using, it may not be using topics. I think I have mentioned that again. Maybe like that can be only understand when we discuss this portion. Maybe I will come back to that, like this section. So this is where the hardware interface things are discussing. So this hardware interface is actually communicating to the controller, but it is communicating not through, I mean, topic, but internally there is a channel. Like maybe I can show you that there is a thing called controller interface. Just a second. You can see here hardware resource interface layer. So using this layer, these controller and hardware interface is communicating. So it is mainly through the APIs. Maybe when I'm showing the hardware interface code, you will get understand. That's why I mentioned I can discuss that like after discussing the basic concept. But
I understand. The main motto of here it is since control manager will use the service methodology and then commands to the controller, and controller will use this
yeah.
APIs.
Uh,
Then it will return back the data or whatever the status it is, right?
no,
So,
no, no.
my,
There is a correction. So
yeah,
the controller
okay.
is not doing anything. Like controller is like loading to the controller manager, and this hardware interface. No, this hardware interface is what like communicating to the controller and the real robot. So this layer we can define. We can write.
Basically,
Yeah.
yeah, this is nothing but our drivers APIs.
Yeah,
You
yeah,
can call
it
it
can
as the drivers API.
we can call it as like kind of I will not say it's kind of direct driver, but I will say it's a bridge between the driver and the
Yeah.
controller.
Or it is a HCL,
Yeah,
hardware
yeah,
abstraction
it's an
layer.
abstraction layer.
Yeah,
So
HCL.
so we can see it here, like from the real robot maybe there will be some driver, maybe some APIs, so that APIs can be integrate in the abstraction layer. So yeah, so this is what the bridging between the controllers and the real robot. So this layer I will be getting back to this because there is a small code that we have to discuss. Okay, so yeah, I think that is clear to you. So the whole concept is that if you want to move a joint in the robot, basically you need to have a controller uh, coupled or like attached into that joint. So the controller can communicate to that joint through a hardware interface layer. That is like an agnostic layer or an abstract layer. Uh, so these are the things that is happening when you interact with a joint in a real robot or in gazebo. Okay, so that is what showing in this diagram. You can see here in the simulation there is a hardware interface. Here also in the hardware on the right side there is a hardware interface, and in the actual hardware there is like real actuators, then embedded controllers which is moving, and when the actuators moves, there will be encoders, wheel encoders, that will be giving the feedback to the hardware interface. And through this through this joints, I mean the hardware interface layer, or in hardware interface layer, this one hardware resource interface layer, it is communicating to the controllers, okay, which is actually loaded inside the controller manager. So that is how each joins in the real robot or gazebo is actually moving. So if
And this hardware interface is basically a ROS, or it is a proprietary based one?
it's
Because
a ROS
I
only.
understand ROS
Yeah,
only,
yeah,
right?
yeah.
Because otherwise everybody will write their own, then it will difficult to maintain the APIs, you know.
Yeah, so
Uh-huh.
we can actually put our driver APIs. For example, if you want to like write,
But driver APIs will be below the this hardware abstraction,
that
right?
can,
Because that is based on the
yeah,
hardware
we
dependent,
can
right?
do both. Actually, one approach is that the hardware interface can talk to the driver layer through topics. Like whenever the hardware interface gets the control commands, it can directly write to the actuator through topics, or maybe you can use some serial communication to the embedded controller. So here, this is the command going to the motor. Okay, so from the controller it is going here, and it is writing to the actuators, right? So there is an embedded controller, maybe like Arduino or some Teensy board or something. So these hardware interface can write some serial commands to the embedded controller. So the embedded controller will set the values, something like that. Or if you set some topics, maybe you can like create a ROS node using ROS serial, and you can communicate over topic as well. For example, if you are using Arduino board here for moving the motors, inside the Arduino board using ROS serial Arduino, you can like subscribe, publish, and everything. So you can simply publish some commands, so that will be going to the embedded controller, and it will move the actuators. Whenever it move the actuators, the encoder will move, and it will be going as the joint state. Okay, so like giving the commands and getting the feedback. Okay, so that is in the actual robot. And for the gazebo, we have a simulation hardware interface, which is writing into the simulator and reading from the simulator. But both can be done using the same controllers. Only difference is that the hardware interface layer, it may be somewhat different. Okay, so this is what actually happening. And in the simulation you can find like the basic model is in the URDF format, and it will be parsed, and it will be like passing, this there is a gazebo plugin, if you remember, called gazebo ROS control, which will be loading this hardware interface. So I will be showing a demonstration of that, so I will be explaining that. Okay, so you will get a clarity. So this is how the controllers working. So just understand that there are different types of controllers in ROS. So I can first show you that ROS control GitHub. If you check it, yeah, this is the main repository for ROS control, and this is having some main packages like controller manager, hardware interface, all this stuff. And you can also find the controllers, list of controllers available from this link. So you can find like there are some existing controllers already available. Like if you want to move the joint in position controller, if you want position controller, there are set of position controllers available here. You can reuse that. Then we have differential drive controller. So if you have a differential drive wheeled robot, you can use the differential drive controller. And Ackerman steering controller, like the car kind of robot, you can control that using this driver. So if you already have that controller now, what you have to do is you can simply load this controller with some configuration, and then it can interact with the hardware interface. Okay, it can interact with the hardware interface, and then like the it can send and receive the join values. So yeah, so this is the advantage of using ROS controller. Like there are different controllers available, meaning here you can see just a second, these controllers are already available. I mean a list of controllers available, so you can simply reuse it, or you can write a new one. Okay, so I will be showing an example of a new controller as well, how to write it. Okay, so before that I will prefer you to check this link, so you will get an exact idea what is going on. Okay, so this is actually from a talk from just a second, and I think they also mention my book here, Mastering ROS. Yeah, that is also good, I think. And this is also from yeah, I think you know France, right? One of our previous I mean team member. So he also have a good documentation about the ROS controller, because the diff board that he have created is based on the ROS controllers. So these documentation actually taken from a ROS talk in ROSCon actually. So I think like France actually mentioned everything in a very detailed way. So this documentation will help, and he's having a good example as well. Okay, yeah, this is actually good. Just a second. So maybe I can follow this, or I can use this one, not this. Just a second. Okay, yeah, this one. So this is what happening. It's very simplified diagram, not very detailed. Like we have robot on the right side. It can be on it can be on simulation or a real robot. Okay, so we have to control it. So in between the real robot and actual hardware, there is an abstraction layer. Okay, that is called the robot hardware interface, and it's actually an agnostic thing. The main purpose of this hardware interface is communication to the simulation and the actual hardware through some API. You can insert your commands to control the hardware and simulation. So the robot hardware interface is connected to the controller. So there are different kinds of controller that we can load, that you already seen. It can be a differential drive controller or ARM controller, like you can define. So that is connected to the hardware interface, and these controllers you can directly interact to this controller. For example, if you want to move a joint independently with your like some topics or something, you can do that. Otherwise, if you want to connect these controllers into some high level stuff like navigation, okay, so what you have to do is, in order to work with the navigation, you have to create a ROS controller for differential drive. If it is a differential drive robot, then the navigation will be sending commands to the controller, and that controller will be moving the robot, something like that. Okay, the same for move it is for manipulators. So the move it will be using the joint trajectory controller, which is actually for controlling a group of joints, and then it will be sending to the robot hardware interface and moving to the actual robot or simulation. So this is what the controllers, I mean, we are using controllers for this purpose. Okay. So I think I have provided enough documentation for this. This link now from France, I think it's very detailed. He actually, discuss most of the stuff very detailed manner. Yeah. And also he mentioning about the hardware interface code. Okay. So I think you got an idea like how the controllers works in ROS. Okay. Just a second, guys. So now we can check the controller in action. Okay. I'm using a manipulator for working with working with the controller to show the demo. I'm using a manipulator. So that example is already there in ROS. It's a very simple demo. I will put the code anyway. It's called RR board. Okay. The RR board is simply a 2 degree of freedom robotic arm, and we are actually attaching the controllers to this joint, and then you are just moving this. Okay. So maybe I can start with the simulation, and then we can see where we are using the controller and all. Okay. So let's start the demo. So I have this code. I think I have taken from this repository or something. Yeah. So you can also set this repository, and we'll get this simulation for a demo. I'm starting the code. The launch file. There are some errors regarding the models, but we can ignore that. Okay, so this is a simulation. I think you have seen this before. I have shown this in the previous chapter. So this is a robot. There is one joint here, and there is another joint here. So these joint will move. Okay, these joints can move, and on the top they have put 2 sensors. Okay, this is actually a camera. This is a laser scan, and you can see the laser scan here. That is just for some demonstration purpose, but we can see the actual thing. So we have the robot ready, and you can see the sensor data here. Okay, sensor data here. The camera view is here. Okay. So the robot is ready, right? So let me try to move this robot, okay, first, and after that I will explain. Okay. So I'm using the controllers. I am actually setting the set points of the controllers, and that's how I'm moving the robot anyway. So you can see how it is moving. So I'm using RQT for this. So there is a plugin called EC Message Publisher, which is actually for sending or publishing topics. And the good thing is that you can select a topics. So currently I am selecting a topic. Just a second. I am selecting the set point of the controller. Okay. We have 2 controllers attached. So I am just selecting the set point of these 2 controller. So this is one controller, joint position controller command. Command is actually for the set point, and state is the feedback. So I am setting command as say one value, and the joint position controller command as another set point. Okay. So the advantage of this plugin is that you will get these kind of thing, like there is a minimum value and maximum value, and you can move the slider, and it will set the set point of the controller. You can see it is so realistic. It's not very, I mean, you can see that controller movement in action, because like when you move, uh, there is an inertia you can observe, right? So yeah, and if we move this, you can see it is moving the second joint. Okay, okay. And by the way, we can also check the RQT graph, so you will get an idea how these nodes are communicating. So basically, this is what it is happening. Yeah, so we have the gazebo, and inside the gazebo you can see the controllers, because it's all loaded into gazebo. The controllers are all working inside. So you can find joint position controller 2, then command and states. Then it's also having the camera plugin and also the laser plugin. So maybe we can close it, and maybe I can explain it again. Two controllers are attached, and you are setting the set points, and that joint is moving. Okay, so this is just a demo, and just check the code. Okay, how is this working? Okay, so I can show you the code, then you will get somewhat clarity how to configure a controller. Okay, I mentioned that there are many controllers already available, and you can simply install these controllers using sudo apt install ROS Noitic, maybe position controllers. Okay, so you can simply search like position controllers, so you can install the position controllers, like effort controllers you can install, then velocity controller you can install, and I think diff drive, yeah, diff drive controller, it's also there, you can see here. Okay, and you can also find the diff board, which is actually the package that France actually created. So maybe we can actually check. You can install it from the Synaptic. That's a good thing actually. If you search for the diff board, okay, yeah, you can see here, this is that project that France actually mentioned, the diff board. This one. Okay, I think this is the project that that we are seeing in the package manager. Let's see, just check for the properties. Yeah, you can see here the maintainer is France. Okay, so he actually put his project onto the ROS repository, so we can install this repository by simply clicking this package. So if you just yeah, so this is a good thing, like after doing the project we can release your project in ROS repository. Okay, yeah, I just shown that. Okay, so coming back to the code, I'm just switching into RR board repository. I can show you the packages. Okay, how we are configuring the controllers and how we are starting it. Okay, so yeah, these are the two packages that we need to work on controllers. So basically the RR board description, I think you know the description is having the URDF file, then gazebo equivalent files, all these things. And RR board control package is simply a configuration package which is having some launch file and the controller configurations. Okay, so let's see what happening when we start this launch file. This is the launch file that we have started. Okay, so when we start this launch file, let me increase the font size. So when we start this launch file, you can find it is starting the gazebo.launch. Okay, and so the gazebo.launch, yeah, after launching the gazebo, it is launching the controllers. Okay, and then it is starting the robot state publisher to start the TF publishing. Okay, and then it is starting the RVs. Okay, so the gazebo.launch now, this first line will be spawning the model into gazebo. Okay, so that is the purpose of gazebo dot launch. Maybe we can see in the launch file this one. Okay, so this is what actually loading the RR board into gazebo. Okay, it is not doing anything, like it is like parsing the URDF file, then starting an empty world, and then this is what spawning. Okay, like we are spawning the robot description that we have stored here as a parameter, and we are like spawning the robot description into gazebo. After spawning, what we are doing is we are starting the controllers. So this is the important part that we have to look on. It's a very easy procedure. If you are using an existing controller, the configuration is very easy. I already mentioned that in order to start the controllers, we need the controller manager. Okay, and the controller manager is already available in ROS. Okay, it's already available. Like when you install ROS full desktop, I think the controller manager will be already installed. So there is a package called controller manager. You can simply check it using ROS CD. You can just use ROS CD controller manager, so you can find the path. Okay, it's already installed. So inside the ROS controller manager, there is a node called spawner. Okay, spawner. So the spawner is what the controller manager. Okay, this is what starting the controllers. Okay, so this is a node actually. You can say, see it here. We are using node. So the spawner will basically read from some arguments. So we can pass like command line arguments. The spawner arguments can be passed. Like what are the controllers that we need to load. Okay, so we can see here join 1 position controller, join 2 position controller. Okay, so where is this controller came from? So that is actually mentioned in the controller.yml. Okay, so if you just check the config folder, you can find this is for the definition of the controller. Definition means what are the controller we need to load. So this is called the namespace. So under this namespace called RR board, we need a join state controller. That controller is for publishing the state of the joins. Okay, join state controller. It is not setting the value. It is actually like reading the state of the joins. Okay, so this may be required for all the robot. Join state controller, publish all the join state, and these two things are the other controller, join position controller and join to position controller. Okay, so this is how the configuration is writing. So inside this join 1 position controller and join 2 position controller, you can actually mention what type of, this is the name of the controller, by the way. You can give any name. Okay, you can give any name, but inside that name you can mention what type of controller it is. it is a position controller or effort controller or any controller you like. Okay, you can mention. So currently it is a effort controller and joint position controller. I mean, effort controller basically means it is controlling using torque value. Inside that we have a joint position controller. So I'm little confused here because we have the position controller with the position controller. I mean, if you check this repository, you can find not this. Yeah, if you check this, there is a position controller folder, then effort controller folder. Okay, so if you take the this plugin.xml, you can find what are the different controller under the effort controllers. Okay, you can find effort controller joint position controller, effort control joint velocity controller, effort control joint effort controller, effort control joint group effort controller. It is for controlling group of joints, and there is a description. Okay, so effort controller joint position controller basically tracks the position command. It expects effort joint interface type of hardware interface. So basically it is for controlling the position. Okay, so I think you can assign any controller, but for a demonstration they are using joint position controller. Likewise, you can find the description of all the plugin from this XML file. So in the position controller, there is again a joint position controller and there is a group position controller. The difference is that in the position controller, it expects position joint interface hardware interface, but in effort controller, it expects effort joint interface. So you may be, I mean, understanding the interface, the effort joint interface from this diagram. This one. Okay, this is the interface. Okay, so effort joint interface is this. Okay, so that is mainly the difference. Okay, so I think just a second. Yeah, so for the simulation, I think we only have this controller available. If you are working for the position control application, we can only use the effort control joint position control. There are something like that. Okay, so the important stuff is that in which joint we are attaching to this controller. Okay, joint 1 and here is joint 2. Okay, so this is how we are configuring a joint with a controller. Okay, so we have to write this YAML file. Okay, like you may have a namespace. Under this namespace we can put all this controller, and you have to pass this value. Okay, so this is where the YAML file is converting into ROS parameters, and you can use that ROS parameter like this. Okay, like you can mention the namespace of the YAML file and the controller name. Okay, so if you mention like this, you can able to load the controller into the controller manager. Okay, so once you load the controller manager, if everything is set, you will get messages like this. Just a second. Yeah, so here you can see gazebo. Okay, controller spawner waiting for service controller manager, and you can see here, I'm not sure you can able to see, loading controller join position controller, loading controller join to position controller, and again controller spawner loaded controllers join position 2, started controller join 1 join 2 position. So if you are getting this message, that means your controllers are properly attached to that joint. Okay, and if you're getting this, then for example, I'm starting the launch file. So that launch file will be simply starting the simulation and also the control manager spawner. And if everything works, you can see the ROS topic list. You can see the topic for giving the set point. So this is the topics that is publishing and subscribing by the controllers. Okay, this is from the joint state publisher controller. This is for the joint 1 position controller. This is for the joint position 2 controller. You can also see the joint state here. Okay, this topic having all the joint states of the robot. Okay, so if you simply publish some values to this, it's actually standard message float 64. If I am simply publishing a value, I'm literally setting the goal of that joint. Okay, I mean the set point. So I'm just setting 0.2, 0.3. You can see the joint is moving. Okay. Okay. So we are simply setting the set point of the controller, and the controller is working and it is sending values to the hardware interface and to the hardware interface to the simulation. Okay, so currently in simulation we are already using a hardware interface. So, I mean, it's already there, that hardware interface. So you can simply define the controllers and it will work. Okay, and this is actually the case of position controller. And in case of a differential drive robot, when we load the differential drive robot like this, it will be loading the controller and it will be waiting for the command velocity or the linear and angular velocity. So maybe I think I have shown the URDF sim tutorial, R2D2. I think I have explained that at that time. Yeah, I'm not sure you remember this. Do you remember this file, guys? This is where we are defining the differential drive controller. You can see here. Okay, you remember the R2D2 robot, right? We have worked with the simulation. So this controller, like we are defining the YAML file, and this is for the gripper, and this is for the head. So we are keeping individual controllers in different file. And if you check the launch file, you can find first we are starting the simulation launch file. So simulation launch file will be spawning the robot model, and this is where we are starting the controllers. So these things are loading the YAML file of the controller, and this is starting the controller manager. Okay, so like you can see here, the controller manager spawner, then argument is R2D2 joint state, then head controller, gripper controller, differential drive controller. Okay, so this is how we can configure a controller. So you can simply take the examples of these thing, the R2D2 and RR board, or the diff board from France. it's also a good example for working with um, yeah, for the controller. Okay, so let me actually check, just a second. So this is a repository. You can find diffboard control here. Okay, inside that you can see the configuration. So in the diffboard control.yml you can find joint state controller, then diff drive controller. Okay, so these are the controllers that he's using, and yeah, then the gazebo, navigation, all the stuff. Okay, so that is how we are configuring the controllers and starting the simulation. In case of I mean, in this project, Franz also done the hardware interface for the actual robot, which is actually in the base code, I guess. Okay, he actually written the hardware interface node, which can able to communicate with the hardware. Okay, but in case of simulation, we don't need to write this. Okay, because it's already there. Okay, yes. So these examples, I think you can actually use. Okay, yeah, and finally, I mean, there are two more topics. Finally, the last topic will be like seeing how to write a custom controller, okay, by yourself. Okay, and the hardware abstraction layer. Okay, so we can start with the hardware abstraction layer. I mentioned that we can communicate to the controllers through the hardware abstraction layer. Okay, so this is actually a code. Yeah, I think it is starting from here. Yeah. The controllers can communicate to the hardware abstraction layer through three interface: effort join, velocity join, and position join interface. And what is the importance of this topic? The importance is that if we want to control a real hardware, okay, real hardware. So the real hardware is ready, and imagine you can able to control a motor by publishing a topic. Okay, by publishing a topic, you have written a ROS serial Arduino code, and that Arduino board is controlling the motor. Okay, and if you publish something to some topic, the Arduino will be writing values to the motor, imagine. And one topic, if you subscribe to one topic from Arduino, it will be giving the encoder value. Okay, so if you create that kind of setup on your hardware, it will be very similar to here. Okay, from the robot, we have an embedded controller which can able to control the actuator, and you will also get the feedback from the encoders. Okay, so if you have these, then you can write a simple C++ code like this. Okay, so you have to define a class called I mean, you can name it. Here it is my robot, and it is inheriting from the hardware interface class. Okay, robot HW, that is the hardware interface class. It's an agnostic abstract layer, and inside that, what you will get is that you will get the values from the controller. Okay, and you can also give value to the controller. Okay, like you can interact with the controller, not directly through this API. Okay, so the good thing is that you will get the current state of the robot. You will also, I mean, can use this value from the controller. You can use the value to the actual hardware. Okay, so so this is actually the bridging code between the hardware and the controller. Okay, and this is a class, right? This is a class, and this class is creating an object here. Okay, my robot space robot, and if you do this, this communication will be happening, like communication between controller and the actual hardware through the robot hardware interface. Okay, so there are some good documentation of hardware interface here. I'm sharing that. Okay, it will be slightly difficult when you start with it, but I think these examples will help you. Okay, basically, we are writing a bridging code. Okay, we are writing a bridging code which can take commands from controller to the actual hardware, then the feedback from the actual hardware to the controller. Okay, just understand that, then you will get an idea. Okay, so yeah, so that is the hardware interface code to connect the robot into actual motors. Okay, and finally I just want to show you a demo. Okay, a demo of the custom controller. Okay, yeah, so let me show you the demo and I will explain. Okay, so if you want to create your own controller, okay, you can do that actually. Okay, there is actually a template for that. Okay, so ROS control boilerplate, if you just simply search, you will get the template for writing a controller. Okay, so what I'm trying to show you is that a sample, an example. Okay, example that you can use to create a controller. Okay, so this is actually the boilerplate, I guess. Yeah, yeah, symbol simulation interface template. Yeah, I can show you an example of that. After that I will explain. Okay, my controller dot launch. Okay, so it's in the simulation, and we can check whether the controller is loaded. You can see here controller spawner waiting for service, loading controller spawner loaded. It's actually loaded my controller. Kalpesh, can you mute your mic? Uh, can you mute your mic, Kalpesh? Okay, maybe I can mute. Okay, so you can see here a robot is moving like one position to another. Okay, I'm not doing anything. I simply loaded the controller, and this custom controller is doing this job. It is actually moving. I mean, you can do anything on the controller. Okay, you can implement some PID loop, or you can do anything. Okay, so it's basically controls the joint. Okay, you can see here we just loaded the controller called my controller, and it is doing this job. Okay, so let's see how the my controller controller is working. Okay, so that we need to check, right? So I'm switching to the controller package, Catkin workspace, and getting workspace. Okay, my controller. Okay, so this is the controller package. Okay, so there is a format for this control package. So this is the last topic. I'm not sure we can discuss the path planner. Maybe this week, if I get time, I can discuss. Okay, I mean next week. Okay, so this is a template for the controller. Okay, so first we can start with the package.xml. It's a basic package, and in order to create your own controller, you need this much of dependencies. Like one important dependency is the plugin lib. So you got an idea, right? Controller is a plugin. Okay, and which is loading that controller? Controller manager. Okay, so we need to have this much of dependency, mainly the plugin lib, then controller interface, all this stuff. And you can see in the CMake list, we need a plugin lib, controller interface, and the plugin is actually built using add library function. Basically, the plugin is not an executable, it's a library actually. So this is how we are compiling that plugin. Okay, it's compiling as a library. Okay, and I can show you the source code, so you will get the template. It's a very simple template. This is the .h file you can find. Okay, and this is the CPP file. I will explain. So basically, in order to write a controller, you need to include the plugin lib header files. Then you need to include the hardware interface, then the controller interface. These header files are mandatory. Okay, now in order to create a controller, you have to inherit from your the interface first. Okay, so what kind of interface that you require? Do you require position joint interface, effort joint interface? So this interface is actually used for communication between controller and hardware interface. Okay, so you have to define, or you have to inherit these controller class with a hardware interface. Okay, and after inheriting, we have to populate this function: initialization, update, starting and stopping. It's very easy. Like what is the thing that we have to do when we initialize the controller? What is the loop that we have to implement in the update function? Update function will be like a infinite while loop. What should we do when we starting the controller, and what should we do when we stopping the controller? Okay, and the join value, what is the join name? Okay, so in the CPP file you can see the function definition. So in the initialization, it is checking for the join value. In order to work with a controller, we need a join value or a set of join values, right? Then only we can work on that joint. So it is checking like whether we got the joined or not. Okay, join means like the join name that is passed along with the controller configuration. So when you define the controller configuration, the YAML file, we have mentioned the join name, right? So that is actually retrieving here. Okay, and this line now, this line is getting the access to that joint. So now this get handle function can able to set the position of that joint. Okay, so we got the joint handle. So in the starting function, we are like getting the initial position of the joint, and in the update function, we are simply implementing a sinusoidal function. Like this is where we are setting the position of the joint using set command. Okay, using set command, we can simply set the position. So when we load the controller, this loop will be always running. Okay, so that's why you can able to see the joint is moving forward and backward. Okay, and in the stopping function there is nothing. Okay, so this is what the controller looks like. Okay, and here is the controller YAML file. So you can see the what controller is actually loaded: my controller namespace, my controller class, and the joint name is elbow pitch joint. Okay, and this is a configuration, and this is the mandatory thing that we have to do when you write a plugin. I think I have mentioned this to you. We have to create a XML file in which we have to mention the namespace and the class and type, then the base class. So we actually inherited from this base class, if you remember, in the CPP code. So after defining everything in the XML, we have to mention that inside the package.xml in the export tag. Okay, then only this plugin will be detecting by the ROS environment. Okay, so this is very important, guys. Just create an XML file which is having all the details of the plugin, then mention in the export tag. Okay, and you have to write the controller YAML, and in the launch file you can find we are launching the simulation, then loading the controller configuration, and we are starting the spawner controller manager basically, and passing the controller name, my controller name. So I know it's difficult to digest, but maybe with this example you will get an idea. Okay, so these are the things that I'm planned to discuss today. So I think you got an idea about the controller, like what is controller and how to configure, what are the existing controllers available, then what is hardware interface, and how to write your own controller. There is actually some tutorials available, yeah, this ROS controller boilerplate is the latest one. So I think this is a good starting point. Okay, I think it's updated, so you can start from here. Yeah, so now we can start with the questions. Let me know if you have any question, guys, regarding the controllers. So if you have any question, let me know. We can discuss. Maybe in the next session we can cover the path planners. Okay, and maybe RQT. Yeah. Okay, so there is a question from Hari. Can we add complex controls like model, predictive? I think yes. So like okay, so if you check this controller code, you can find this class, right? So it's our logic, like you can implement anything. You have the joint control. Okay, you can send any value to the joint. Okay, and also you will get the current position of the joint. Then it's your logic. Okay, you can implement any kind of controllers in this template. Okay, so that's what, like there are some existing controllers available. If you want to implement new thing, you can use the template. So, yes. Any more question, guys? I will prefer, or I mean I will say just go through the list of links that I have shared with you. I think I have shared a lot of content, so just go through it and create make an idea. So I can also share the video of that ROSCon talk. So this is explaining the ROS control in detail, and this is the PDF of the slide. So we can see these diagram that we have discussed. Where is ROS control using, and here we can see controllers are decoupled from the robot, and this is for hardware interface. This is an abstraction layer. This is a complete picture. Yeah. And they are also discuss some relative yeah. So they actually presented in a very good manner. Yeah. Any more question, guys? Any more questions? Okay, so if you don't have any questions, I think we can conclude today's session. So thanks for attending, and see you next week. Let me know, like, if we have if I get more time. I'm planning to finish the ROS 1 this month, or like in the mid of Jan, and then we can start with ROS 2. So I'm not sure, maybe if there are some outdated topics, then maybe we can ignore it, like the RAS. Let me check if there is any outdated topic. After that, we can start with the migration of ROS 2. So that is what the important topic. So next week we will be seeing the path planners and RQT plugin. Okay, and yes, so thanks for attending, guys. See you next week.